So I just introduced you that the total variation in the dependent variable, the variable you want to explain, its variation can be decomposed into explained part and unexplained part. So then you can think, and it's given in the result, and then it is natural to think of their ratio. How much is explained? We call that coefficient of determination. So how much of y is determined by the regression model, and it is usually denoted as r squared. So r square, the term r square is more commonly used than coefficient of determination. So I never heard about the name coefficient of determination like elsewhere, but usually I call this r square. And r square is the ratio between regression sum of squares out of total sum of squares. So this is the ratio of, so explained, this much is explained out of this much. So that's the ratio. As it approaches to 1, as it converges to 1, you are explaining most of the dependent variable. If it is close to 0, then you are not explaining anything. You cannot explain nearly none of the nearly 0% of the dependent variable. So this measures the strength. Again, how much you can explain or how small the residuals are. So the smaller the residuals are, the more you explain, right? So it captures the strength of the relationship between x and y. There are some, so in our example, Alljust Square was 0.9307. Let me see. This is the r square coefficient of determination. Already it is written as r squared. R square is 0.9307 approximately. Let's put it 7. Then this means 93%, approximately 93% of the variation in y is explained by the regression model or by the independent variable. And the other remaining 6.94 is unexplained. And I didn't show you this. And remember, the sum of squares are given here, and you can simply check that sum of these two guys should be the total sum of squares. Sum, right? So when you add these two guys, you always get the total sum of squares. So it's mathematically proven. And r squared, another y, then y it is denoted as r squared because alternatively you can obtain r squared by calculating the correlation between actual observations and the fitted values. Remember, you have fitted values as many as the actual observations, so you can calculate their covariance, correlation, and covariance, whatever, right? So you can obtain the correlation, and r square happened to be its squared, because r square was defined by sum of squares, so you have to square the correlation here, right? And the correlation is given. Correlation is also given here. Multiple r itself. This guy is the correlation between the actual value and the fitted value. And just to see what happens if you square this, square that, this is that, right? As it should be, these two guys are the same. When you take square of multiple r, you get these. Okay, and in an extreme case, if r square is 0, that means there is no linear relationship, or x is the regression line is flat. Regression line is flat, so there is no variation in fitted value. right? You say the same number for anyone. So I ask you to predict the hourly wage of a person, and no matter who they are, you always say like $40,000. So that's that you are not explaining anything. That's when R square equals to 0. Or when correlation between y and y hat equals to 0. And if R square is 1, it's perfect. Again, it's perfect case, and all data points line up on the straight line. Perfect. There is no residual at all. So remember, R square is a percentage. It always lies between 0 and 1. 0 and 1. And closer to 1 means the model explains better, and closer to 0 means the model is not explaining anything. And here I just explained. Then what is the adjusted R square? Adjusted R square is, as you can see, it adjusts something. What does it adjust? It adjusts for additional variable. So I considered only one variable, like say to explain hourly wage. I considered education only, or to explain total cost, I used output only. But you may think about different variables, like for example, to predict the cost, say you may want to consider say sales tax rate, or the price of say a gas or water bill rate. So many different things uh, are relevant to the cost, but I'm using only one variable. When you have more than one variable, then you may want to adjust the R squares. You may want to use adjusted R square, which make different models more comparable, right? So like you may have two models, and you want to choose who is doing better. But say model A considers 100 variables and model B considers only 10 variables. Then in that case, comparing them one on one is unfair. So you have to adjust like pound for pound. That is adjusted R square. You have to use same number of, if you use the same number of variables, you could explain this much, something like that. Anyhow, still R square, it's another kind of R square. Uh, and let's think about the education. Education example is here. We had education and hourly wage, and the sample size is more than 2200. And let's do it. Regression. Y range is here. X range is here. And first label, I'm not going to use plots. Then you get the results. From here, remember in this example, realistic example, multiple R is about 0.32 and R square is only about 10%, right? R square is only about 10%. You may be very disappointed by this, but actually not. Think about this. We are predicting hourly wage, and intuitively there are a lot of components going into the hourly wage determination. So education is an important factor, but there must be many more determinants of the wage. So 10% is not a bad number. You are explaining 10% of wage only using one variable. So I think I think in some sense it's too good. Education explains 10% of the wage. Okay. But anyhow, it's not bad. It is common in many analysis. Like around 10% is not that bad. Like So don't be disappointed too much in real data analysis. So then alternatively, if you want to improve this, you may use more variables. So I'm going to extend the regression equation to include another independent variable. Say x2 is included here, and then when you have only one independent variable, we call that the simple regression model. But when you have more than one independent variable, we call this a multiple regression model. So simple regression to multiple regression. In that case, most of the results hold in the same way, but the interpretation is a little bit different. First, beta 1. Here, beta 1 is the slope. So when there is no x2, simply beta 1 was the change in y when x1 changes, x1 increases by a unit. So when x1 increases by 1 unit, beta y increases by beta 1. That was the meaning of beta 1. But when you have x2, you have to put this condition. So same, when x1 increases by 1 unit, y increases by beta 1 under the condition that x2 is fixed. x2 does not change. So ceteris paribus assumption. All the other guys don't change. And then let's compare what happens when x1 increases and how much y increases. So that's a subtle interpretation, but important being fixing something. So it's like control group and experiment group. So fitted value is calculated this way, which is obvious. So use estimates for beta 0, beta 1, beta 2, because you cannot predict the error. Of course, error is assumed to be 0. You ignore that in prediction, fitted value. Residual analysis is the same. Sum of squared errors calculated the same way. Least squares calculated in the same way. And regression sum of squares and total sum of squares, R-square, everything is calculated in the same way. Because in those analyses, we do not use x1 or x2. X is not important. What was important in those regression analysis was epsilon hat or y hat. And once you obtain the fitted value, all the following analysis can go in a similar way. Of course, there is a little bit mathematical differences, but I'm not going to show them. Then here, I consider additionally I include age. So to predict hourly wage, I consider your age and education, how old you are and how much you are educated. So then answer this question. Consider a person who's 30 years old and 16 years in school. What is this person's predicted wage? Try this and come back to the next video.